Now it started. Is the audio bouncing? Can you sing a la 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 la? Okay, excellent. Well, I'll begin with a word of prayer. So, Heavenly Father, we thank you for this day. I thank you for the students. Just ask you to just bless our work today, Lord. In your name I pray. Amen. Okay, so let me just recap what we know. What was the main result? Given a matrix A in over some field, there exist elementary matrices E1, E2, Ek, such that the reduced row echelon form of A is equal to Ek, Ek minus 1, E3, E2, E1, A. In other words, if we're doing a row reduction on a matrix, we can achieve that row reduction by successive multiplication by elementary matrices that correspond to the same row operations as we do in the Gauss-Jordan elimination. All right, the same thing. So this is always available to us for any matrix. We can take any matrix, we can calculate the reduced row echelon form of it, and we can achieve that by multiplying elementary matrices on the left as such. All right. Or, of course, you could summarize this by saying E, call this whole thing E, and so we got is EA, right, where E is a product of elementary matrices. So this is the main result I was hoping Dr. Smith would communicate with you last time, and I think he did. All right? So it turns out that this is terribly useful for understanding many things, first of which we'll attack is the theory of invertible matrices. So I've already told you some basics of invertible matrices. Like what do we currently know about invertible matrices? So let's just remind ourselves. So our definition was a square matrix, right, is invertible with inverse A inverse, and we could call that thing B for the sake of discussion, if and only if what? AB is equal to I is equal to BA, right? To state it in a less awkward way, if there exists a B such that both AB is equal to the identity and BA is equal to the identity, then that matrix A is said to be invertible, and the inverse of that matrix is B. Right? And we proved that that was unique. What else did we prove about inverse matrices? Anything else? Just a few basic properties, right? We proved, for example, that AB inverse is equal to B inverse, A inverse, right? If A and B are both invertible, then the product is invertible, and that's the formula for its inverse. I also mentioned that if we have a constant, a non-zero constant, and A is invertible, then CA is also invertible, and guess what? The inverse is 1 over C times A inverse, or perhaps I should say C inverse times A inverse, with the understanding that, C could be in Z mod a prime, so then we'd have to understand the multiplicative inverse in the sense of calculation mod 5 or mod 7 or whatever. These things we know. Anything else we know about invertible matrices? At the moment, not really. All right. One thing we could do is we could use induction to do, instead of just the sock shoes formula, we could do the sock shoes formula, right? So by induction, we could prove that if we have A1, A2, an, all invertible, all right, then their product, A1, A2, an inverse, is equal to an inverse, a2 inverse, a1 inverse. All right, we could prove that with an induction argument. I proved a similar theorem for the transpose of a bunch of matrices multiplied. So the induction here is nearly identical to that. All right. These are things we know. So a new thing I should share with you is how to solve several systems at once. All right. And what I mean here is I'm saying not just any old, okay, if the systems are genuinely disconnected, all right, if you give me, you know, hey, here's 3 equations and 5 unknowns, here's another 7 equations and 13 unknowns, solve them, right? What would you do? Just solve them separately, right? And then that's the solution, you know? But if the two systems of equations are linked, if they have the same coefficient matrix, then maybe we can solve both of them in the same way, right? So like if the systems that we're looking at are something like AV1 equals to B1, and, you know, AV2 equals to B2, right? AVK equals to BK. And so each one of these, we're talking about M equations in N unknowns. All right, so what size is A? It's a well, it doesn't have to be square. I mean, I would say A is M by N, right? B, how big is B? B is a what? It's an M vector, right? It's as big as there is a number of equations, right? So I'm saying, notice I'm using the same A on every last one of these. So they all share the same coefficient matrix, but maybe they've got different inhomogeneous terms. How would you solve the first one? What would you do? We know how to do it. We calculate the reduced row echelon form of A with B1 slapped on, right? What's that going to give me? Well, let's just say it's going to give me R1. All right? It's going to give me some row-reduced matrix, right? And from that row-reduced matrix, we could read the solution. We know how. Special case. If it happened to be a square matrix, right? And it happened to be consistent, what would this look like? What do we get? We get the identity matrix, right? And what's the last column become? V1, right? Indeed. So we can just straight up read the solution off the last column if we're dealing with the case of as many equations as many as unknowns, and it happens to be consistent, right? But that's a special case. Generally speaking, we got to run through the parameters and the dependent versus independent, blah, 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 blah. How do we solve the second system? Again, right? You'd look at the reduced row echelon form of A with B2 slapped on it. That would give us an R2, and we could extrapolate the solution from this, right? Sticking with my special case, right? Sticking with my special case once more, if it happened to be the case that, again, for system 2, we had as many equations as many unknowns, then what would you have? You'd have reduced row echelon form of A with B2 simplifies to the identity matrix with V2, right? And this continues, right? So finally, likewise. So okay, what about elementary matrices, right? So I mean, there has to be an elementary matrix which does what? E, which again, product of elementary matrices, such that what? Such that, E times A with B1 slapped onto it gives us what? Yeah, this thing, right? In other words, that's what I've called R1, right? So here's my question. What if you think about the row operations for system 2? What governs the row reduction? How does Gaussian elimination work on a system? I mean, you could think about it going left to right, right? We could do a modification of Gaussian elimination which just cleared out each pivot one at a time and just kind of swept across, and what would happen? Yeah, well, you left the ones and zeros. There could be a non-pivot column in there somewhere. It's possible, right? But certainly in the consistent case, the last row wouldn't be zeros. But if you think about it, at least ignoring the last column, right? Ignoring the last column, we could. See, I want to assume, let's assume it's consistent, all right? That's just to keep things from, there's going to be like a lot of clutter if I try to explain what I'm explaining in the inconsistent case, all right? Assume these systems are all consistent, then we can say that, we can say the following. If they're all consistent, we can say, well, the same row reduction will do the second system, right? So like I can do E with AB1 equals R2. And so forth down the stack. I can do E times A with BK is the reduction of the last one. I can solve all these systems with the same strategy, the same set of row reductions, and hence they multiply by the same elementary matrix to get the RREF. Yep. Oh yeah, B2. Thank you. But what else? Okay, so fine. But the thing is, we have this system of equations, matrix multiplications, right? You can group these together and write them as one equation. See, this is really, well, I'll do it to start with. It's E times A B1, and then E A B2. Glue it together all the way to the last one. Well, oh, stink. Sorry. Sorry. Okay, so any one of these okay, so generally speaking, if you look at the jth one of these, E, A, B, J, what does the column by column matrix multiplication say? I mean, we could bring it in, it's like E times column 1 of A, right? Fine, I'll do another step here. So that's column 1 of A, right? How many columns does A have? n, all right? Remember, we have a column-by-column matrix multiplication rule. So I can take E multiplying the outside, and I can multiply each column one at a time, the column by column. You guys proved this in homework 1, yeah? You skipped the proof of this in homework 1. I'm not sure what the case may be, but this was something you were asked to prove in homework 1, was that we have this column by column multiplication rule. I think it was in your homework 1. I'm not done the grading yet. I'll find out soon. Don't answer me if you did it or not. That's my grade. I got a grade, right? Okay, so great. But this, of course, we could rewrite as just EA and EBJ. So the point I'm trying to make is the following. Consider the following matrix. We want to think about A, then we'll glue on B1, B2, BK. So we look at this so-called super augmented coefficient matrix. So instead of gluing on one inhomogeneous term, you glue on k of them. The really neat thing is, if we multiply that by E, right? What's this give us? By the row by column matrix multiplication rule, right? So, but you notice that R1, R2, all the way on out to RK, the first n columns of those, they're the same. These all share same first n columns. Notice that, yes, bless you. Notice that this proves that. See, because EA, BJ, what happens in the first n columns stays in the first n columns, right? It just reduces to EA. Yeah? So, what I'm trying to say here is we can read, like these two together. If I put these two together, what is that? That is the reduced row echelon form of, A with B1 slapped on it, assuming it's consistent. So what I'm trying to say is you can solve all k of these systems at the same time by doing one row reduction and then reading column by column in the super augmented reduced matrix. And it's easiest to understand it when we have the same number of equations as variables, because then if it's consistent, then this E here will actually, well, let me shut up. Let me not say it too much. So this is the theorem. To solve AV1 equal to B1, AV2 equal to B2, AVK equal to BK, calculate the reduced row echelon form of A with B1, B2, BK, and read off solutions by examining last k columns. inappropriate way. This is not a very formal mathematical theorem. This is more of a piece of calculational advice, yeah.
So if you're dealing with a system that has many more equations than variables, begin the row reduction, you might not get to the last row of the matrix before you run into the B column.
Mm-hmm.
Just stop there and don't reduce the B column.
So if the row reduction continues to the B column, that means that the system is inconsistent. That means that the B column is a pivot, which corresponds to there being an equation 0 equals to 1. So if I assume it's consistent, that doesn't happen. But you're right. If the row reduction continues into the B columns, that still won't change the row reduction of the first n columns. It's just that to get to the reduced row echelon form of the answer, I might need something other than what I've called E here. I would need E with a few extra operations to actually reduce that later column down. So the algorithm still makes sense, actually, even when it's inconsistent. It's just that if one of these systems is inconsistent, when you look at the row reduction, you're going to get, let me just put down it's much easier for me to answer his question with a specific made-up thing. So if I calculate, it, and don't ask me for the original matrix, but if I had some original matrix, you know, A with blah, 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 and blah, blah, blah. Okay, suppose this is 3 by 3, right? And so three equations, 3 unknowns, and 3 systems like that. Okay. Tell you what, I'll make it 4. Just so we don't confuse the 3. Pac-Man. And suppose it ends up being this. All right. The first Pac-Man's whatever. I mean, it's here, this would be a 3 by 4 matrix. 3 rows, 4 columns. Each one of those star, 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 star in Pac-Man are in homogeneous terms to 4 separate systems. The 4 separate systems I'm solving are, you know, AV1 equal to star, AV2 equal to star, star, AV3 equal to star, 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 and AV4 equal to Pac-Man. So these 4 systems can be solved simultaneously by this one row reduction of the super augmented matrix. So hypothetically, suppose I gave you specific 3 by 3 matrix, I gave you a specific set of 4 in homogeneous terms, and it worked out like follows. So I mean, I think that's a reduced row echelon form, yeah? Can that be row reduced? It cannot. The pivots are all E1, E2, E3. That cannot be. If that's where the Gaussian elimination leads you to, that's where you're done. All right? And so 3 of these systems are consistent, and one of them is inconsistent. Which one of those 4 systems is inconsistent? Right, the star-star. Because to see the star-star solution, you have to focus your attention. So star-star was this, and that led over to this, right? So you can take from this and read that the star-star equation is equivalent to x equals to 0, y equals to 0. Well, wait a minute, excuse me. Rather, the end of the star-star would be like x plus y equal to 0, z equals to 0, and 0 equals to, oh no, 0 equals to 1. That's a drag. So that's the star-starry system is equivalent to that system, which of course is inconsistent. But in contrast, the first and the third and the fourth systems would be consistent, and I could read the solution off of those, right? What would the solution be for the first one? Let's say it has v1 equal to x, y, z, where what's x equal to? Well, I should say x plus y is equal to 1, right? This says that z is equal to 2, right? And the third row gives me no information. But what this says is x is equal to 1 minus y. So in fact, v1 would be an element of the following solution set. 1 minus y, y, 2, such that y is real. I'm keeping it real, if you don't mind. So in fact, there are infinitely many solutions. Any choice of y gives me a solution to AV1 equal to star. The star-star equation has no solutions. Would it help? Let me actually go on. So that's, I have an explicit example in the notes, all right, which we'll look at here, hopefully towards the end of class. All right, great. So now we can solve more than one system of equations if they share the same coefficient matrix. But you might wonder, why do you care about that, right? Why does that matter? Well, let's look at the problem of calculating the inverse matrix, right? Let's look at that problem. Yep.
How'd you get y?
We always use the non-pivotal variables as a parameter for the solution set. So in this case, x plus y is the non-pivotal variable. So, I mean, y is equal to y. Why not?
Okay.
You can't argue with that.
No, you can't.
No, but it is our custom. You got x plus y equal to 0, right? You got two choices, y equals minus x or x equals minus y.
Okay.
So we choose, oh, you're asking why did I have that 1 there? The answer is no good. Oh, wait a minute. Stupid. Up here. Don't look here. Up here. So that's coming from this one. That x plus y equals to 1, rather. So I can either put y equal to 1 minus x, or I can put x equal to 1 minus y. I put x equal to 1 minus y because, again, y is not the pivot variable. Y is the non-pivotal variable, and we use non-pivotal variables for our parameters in our solution set.
But how'd you get x plus y? I'm so lost.
I'm assuming that the original system has variables x, y, z.
Yes.
So in my nomenclature, this is x, this is y, this is z. So looking at this right here, x plus y equal to 1. Y is not in the pivot position, so I use it as the parameter of the solution set.
Okay. And then did you just pick that first column just because you could?
Yes.
Okay.
We could have also looked at the third or the fourth column. Those would be different solution sets. Yeah.
Awesome.
Yep, yep. Okay, so as tempting as it is for me to actually do that, let me go on. So here's the question. Given A, which is, say, an n by n matrix over a field, can we find A inverse, right? How do we calculate that? All right. So let's look at what that means. That means that A times A inverse equals to the identity, right? It also means that A inverse times A is equal to the identity, but let's focus our attention on this part of this half of the puzzle, all right? So let's call the thing we don't know. Let's call A inverse equal to V1, V2, Vn, right? Just denote. Then what are we looking at? We're looking at A times V1, V2, Vn equal to E1, E2, En. wait a second, what is this? In other words, we've got AV1, AV2, AVN, like that. Which is to say, to find the inverse matrix is actually to solve n equations in n unknowns n times. But those n-fold problems all share the same coefficient matrix, namely the matrix which is given A. See, this is the same as solving AV1 equal to E1, AV2 is E2, and so on down the line. But we know how to solve a bunch of systems which share the same coefficient matrix. Right? I just gave you the algorithm, so how do we do it? So we consider the reduced row echelon form of what? A with E1 and then E2, En. This, to solve all n equations at star, as I'm calling these. We just need to calculate the reduced row echelon form of that. This is that special case. Each one of these is n equations and n unknowns, right? So if it's consistent, the first n columns of this row reduction must be the identity matrix. So if in fact A inverse exists, this will work out to the identity matrix and then V1, V2, Vn. By the theorem that I just stated. In other words, to calculate A inverse, if it exists, we'll find the reduced row echelon form of A with the identity matrix concatenated on the end will be equal to the identity matrix, and whatever appears here is the inverse. Likewise, if the reduced row echelon form of A with the identity matrix concatenated on is not equal to the identity matrix times something, right? If it's not equal to the identity matrix times something, what does that mean? What's that? It either means the last row is all zeros, right? If that's the case, that means that the solution's not unique, which won't work for us because we already proved that the inverse matrix is unique. So that's out. Or it means that there's a non-zero column in the star part, which would correspond to one of these n systems being inconsistent. So again, there's no inverse. So in summary, in either of those cases, this implies A inverse does not exist. So in short, if you just take the matrix you're given, slap the identity matrix next to it, row reduce that thing, it will tell you categorically whether the inverse exists or doesn't. And if it does exist, it's sitting there waiting for you to just copy off the matrix, the reduced matrix. There's more. Notice if A inverse exists, right, then E times AI is equal to I with A inverse. What does that show you also? Where E is the product of elementary matrices which achieves the row reduction, right? So the column by column matrix multiplication says that this is EA and then EI which is also known as EA, E equals to I, A inverse. So what does that tell you? I'm assuming A inverse exists, so that would, yeah. But what does this equation show us here? Two things, right? EA is equal to I. Right. Or how about AI? I should really do this one and that one, right? You're right. You're right that EI is equal to A inverse. I don't disagree. That's good. But what's more interesting is that E is straight up equal to A inverse. That is true. A side benefit of this is what Nathan just said, which is, Nathaniel? Nate? Doesn't matter. What it doesn't matter said is that, I'm sorry, to be clear, what it doesn't matter said is that since E is a product of elementary matrices, it follows that the inverse of A is a product of elementary matrices. But if we invert this equation, then E inverse is equal to A. But E inverse is a product of elementary matrices is, again, each one of them is invertible. So it would, once you have this, you can get that the product of that A is a product of elementary matrices and the inverse of A is a product of elementary matrices. These things are all true. So we start to obtain a list of equivalent statements for an invertible matrix. One of those being that if a matrix can be written as a product of elementary matrices, it's invertible. Right? In fact, that's an if and only if. Okay. There are some theoretical tidbits I should put on the board here because I have gone astray a bit, and so let me just try to. There's another. I have no regrets about what I've shown you, but I need to share something else with you. Any questions before I engage in a cover-up? Well, you Liberty students, you're often disinterested in cover-ups. Should be more interested. University students should be interested in truth. Is that controversial to say?
That we're interested in truth?
Yeah. Shouldn't be controversial, right? No, okay. In your alternative. You can have your alternative truth. You just can't have your alternative facts. No, I forgot. I don't know how this works. Oh, lest I forget. I wish I could forget. That which I cannot forget. All right. So, maybe if I had another, I don't know, hour to prepare for class beforehand, there exists a chance I could weave this all together and do it in all one smooth, uniform dialogue. But I think it's healthy for us to kind of stumble through this a little bit and sort of discover it bit by bit. But that said, certain theoretical goals have not been accomplished in this lecture yet, which are important to us for certain questions. The first one of those being my lemma 3.6.1, which says the following kind of surprising thing, I suppose. It says that AX equals to 0. Well, first of all, AX equal to 0, is this consistent? It's a homogeneous system. Is it consistent? It is consistent, right? A times 0 is 0, so it's always consistent. Right, if the only solution is 0 to ax equal to 0, we're talking about n equations and n unknowns, that in fact implies what? Well, here's my first lemma. If the solution of ax equal to 0 is unique, if and only if the reducer echelon form of A is I. So I prove that. Okay, so the proof is basically just by row reduction. I don't really have much to say here, except that we have, this is one of the lemmas we know. I suppose the other direction, if the reducer, if you know, starting on this side, if RREF of A is I, that means that I have elementary matrices, right, E1 through EK, such that when I take EA, it simplifies to I. But of course, when I take E on 0, it simplifies to 0. And this is the reduced row echelon. So this is the reduced row echelon form of the augmented coefficient matrix of A by 0. And of course, we can read from that that the solution to that is 0, and that's the only solution. So that's the converse direction. You notice the role elementary matrices played there, though. Like, how would you formulate that argument without elementary matrices? You could do it, but you'd have to do it through a paragraph of writing about row reductions, right? That's the thing. Elementary matrices allow us to replace prose about row reduction with an equation for elementary matrices, which is really, really nice. Next up, the reduced echelon form of A is equal to I if and only if A is the product of elementary matrices. So let's see here. How did I prove that? I proved it a different way. I mean, we've already proved that. I think behind that, in the cover-up, it might already be implicit with what I put on the board today, is my point. But here's a separate proof of it. First of all, if the reduced echelon form is the identity, then there has to exist a product of elementary matrices such that EA is equal to I, right? And then you can just multiply by the inverse, which exists because, again, going back to this, each elementary matrix is invertible because row operations are reversible, and hence the inverse exists. And it's this, but then by the sock shoes formula, we get that. And then that shows that A is the product of elementary matrices. Now, vice versa, if we suppose A is a product of elementary matrices, then we can take A and multiply by these elementary matrices, and in so doing, get the identity matrix. But that proves that the reduced row echelon form of A is the identity, right? Because if you can do row reductions, which is what these are, and you can row reduce to the identity matrix, well, game over. That's the reduced row echelon form of A, right? Again, going back to last class. So there's another lemma. Corollary 3.6.3. I said, given the two lemmas above, the following is immediate. So these are three characterizations of invertible matrices. One is that the zero, the homogeneous problem has only the zero solution. Two, that the reduced row echelon form, B, that the reduced row echelon form is, of A is I. And finally, C, that A is the product of elementary matrices. How do you get from, like, oh, we've already proved A and B being equivalent was the first lemma, wasn't it? B and C being equivalent was the second level lemma. That's why we have A is equivalent to B is equivalent to C. It really is just pure logic, right? If A and B are equivalent and B and C are equivalent, then A and C are equivalent, right? Theorem, A is invertible if and only if A is the product of elementary matrices. So here's the thing that we haven't come up to yet, is you notice in our definition, we had that the inverse satisfies both AB equals to I and BA is equal to I, right? So when I say that A is invertible, if and only if A is a product of elementary matrices, that means I need to show that there's a product of elementary matrices that multiplies on the left or on the right that makes that gives you back the identity if I wanted to go directly from the definition of invertible. So what do I do? I'm not sure. Well, I guess the forward direction is simple. If A inverse exists, then you hit AX equal to 0 with A inverse on both sides, and out you got X equal to 0. That's the only solution. Bam. Because once we know that X equals 0 is the only solution, then we know by this up here, oh, A is a product of elementary matrices. Woohoo! How about the other direction? Suppose A is a product of elementary matrices, right? Like here. Then I point out that the product is invertible, right? By the sock shoes, and there you go. I seem to have still dodged. I just dodged this issue, didn't I? I didn't deal with it yet, did I? So that's my next order of business, because why check two things when we can just check one thing, all right? So what this theorem says is that if it's a left inverse, it's automatically a right inverse and vice versa. So it actually suffices to check that BA is equal to I, or it suffices to check that AB is equal to I to get that A is invertible. But the proof of that's kind of a pain. So, I mean, here goes. Suppose you've got BA is equal to I. Now, if AX is equal to 0, then we can multiply this equation by B on both sides. It gives us BAX equal to 0. Remember, BA is assumed to be I here. So IX is equal to 0, which is to say X is equal to 0. That shows that the only solution to AX equal to 0 is what? 0. That tells me that A inverse exists by the previous theorem, right? And furthermore, we can multiply BA equal to I on the right by A inverse to find that BA inverse is equal to I A inverse, so B is equal to A inverse, and there you go. And vice versa. If we have AB equals to I can look at BX equal to 0, multiply both sides by A. I get that 0 is the only solution, therefore the inverse exists. And we can prove that that inverse, again, has to be, you can get that BA has to be equal to I given the existence of the inverse. So long story short, in the proofs before this point, I've always been like, here's the proof that BA is equal to I or vice versa, and then I always say, oh, the other one's similar. Part of the reason I did that is because I know that the other half of the proof we don't even need to give, because eventually we learn that to check that a matrix is invertible, it suffices to check either this condition or that condition. We could use one or the other, right? This is one of those results where we just use it going past this point in the course, all right? You don't have to say by proposition 3.6.5. It's understood. This is part of the culture of linear algebra, knowing that it suffices to check one side of the inverse, all right? I shut up. Another theorem we have is that if A is invertible, all right, then for each B, the system of equations AX equals to B has a unique solution. And conversely, if AX equals to B has a unique solution for every possible B, then A inverse exists. So this is another way of characterizing invertibility. If the equation AX equals to B has a solution for any possible choice of B, that means A is invertible. This is not surprising, because if you just let B cycle through E1, E2, E3, E4, En, those were the n equations that we needed to solve simultaneously to calculate the inverse. I mean, we know that even if you can solve just those n problems for the standard basis playing the role of B, we found an inverse. So it's not surprising that if it's true for all possible B, the inverse exists. But here's the proof. We're almost out of time here, so I'll let you read that. And then I've actually been focusing today on the calculation of an inverse matrix earlier. So here's an honest-to-goodness example. three equations, two sets of three equations and how many unknowns? Two, right? So here's the augmented coefficient matrices. Here's the super augmented coefficient matrix. The reduced echelon form of it's that. And so you can read off the solution -1 and -2 for this one, x equals to 1 and y equals to 1 for that one, from that single sweeping calculation. These dot, dot, dots, why is that there? Yeah, it's to separate the coefficients from the inhomogeneous terms, but the more honest answer is because I stole this from my brother's handout. And he uses dots instead of bars. So here's finally, I should at least give you an honest to goodness calculation before we leave today. Here it is. This matrix, here's A, and actually before in the notes I showed the row reductions, which reduce to that. All right? Well, reduce to that. And so what the theorem we did today says is that is the inverse matrix to A. That's it. And so you could try it out. You could multiply this matrix times that matrix and see that you get back to identity. You'd find out it works. See if I have any others here. And that brings us to the end of Chapter 3. You notice here there's a handy-dandy flow chart for Gaussian elimination. Don't look at it too carefully. It's at least the spirit of it is correct. If not the letter of the law, the spirit of the law is correct. I think it's correct. I'm not an algorithmics kind of guy, though, you know. You're all fans of the algorithmics. It seems like it could be a band, right? I don't know. Maybe. No? You guys are...
Whatever your heart desires.
If you dream it, you can do it. What if your dreams are nightmares?
You don't have to do it.
Oh, okay. All right. Anyway, thanks. You can turn off the. I've said what I have to say.
Have a good day.
Yeah, you too. Thank you.